Hello, good afternoon. I hope you guys have had a good day. We are going to look at sections 1.1 and 1.2 in this video, and they deal with graphs, intercepts, symmetry, relations, functions, domain and range, piecewise functions, zeros of functions. That's that's kind of getting you into the whole unit, but these are things that you talked about in Algebra 2 with trig also. So these sections are just a basic review. Hopefully you will remember most everything you see in here. All right, in section 1.1, they go back over graphing. So in pre-calculus has a lot of graphing in it, and you're going to see a lot about relations and functions in every chapter. Chapter 2 is going to be talking about quadratic functions, polynomial functions. Chapter 3, we look at exponential functions, logarithmic functions. Chapter 4, we start studying about trig functions, sine, cosine, graphing, those which we kind of dove into in Algebra 2 trig at the end. The Cartesian coordinate system is named after René Descartes. The x and y coordinates of a point are called the abscissa and ordinate. There are other coordinate systems we'll talk about later on, such as the polar graphing coordinate system, which you've never seen before, and that's later on in chapter 6. Very neat. Those graphs are pretty cool. By the end of this course, as you prepare for calculus in college, you should be familiar with a variety of parent functions. Parent just means that it is the basic graph. It has not been transformed in any way. So for example, basic parent function of a quadratic function, y equals x squared. If you say y equals x squared plus 2, then you're translating that graph. So y equals x squared would be your parent or identity function. You will learn by the end how to translate, reflect, rotate. You need to know all these different functions, what they look like graphically, as well as what they look like algebraically. So going back over the rectangular coordinate system, recall, of course, is divided into 4 regions known as quadrants that go in the counterclockwise direction. Graphs of all equations into variables, most commonly you see x, y, are the sets of points whose coordinates satisfy the equation. So what that means is, let's say we've got this function, y equals 3 minus x cubed. Any x, y value that you plug into this equation and it creates a true statement is a solution and satisfies that equation. Also, that ordered pair would be on the graph of this function. So let's take an x. For example, let's take -1. All right, so we're going to let x be -1. And just simply plug in, so you have y equals 3 minus -1 cubed. Please be careful when you are raising negative values to an exponent. I see a lot of common mistakes in that area. So here, 3, you've got -1 cubed, of course, becomes, first stays -1, and that becomes 4. So the order pair, -1, 4 would satisfy this equation and be a solution to that equation is what you would state. All right, like I mentioned, parent functions a minute ago, parent functions are sometimes called identity functions. Both terms, as I previously stated, simply mean an original graph or function that has not been transformed in any way, has no values that have been added, subtracted, multiplied, or divided. If you'll notice, in each of these graphs we have here, these are some basic parent functions you should be familiar with. Cosine, sine function, Rational function, we get to rational functions in chapter 2. I discussed exponential logarithmic, chapter 3. These functions, you see no value added or subtracted to x, which would create a left or right translation or slide. You see no value multiplied or a fraction multiplied, which would also indicate division to x either. And that would create, of course, your reflections. If it's a negative number multiplied to x, it would create your shrinking or stretching vertically, horizontally. But you see none of that. So when you hear parent and identity, just remember that is a basic graph. It hasn't been translated anyway. So you got your linear function that you see, your quadratic, cubic, sine function, and so on. All right, as you recall, when you first learned a graph, I'm sure you did it by what's called the point plotting method, and your teacher more than likely had you create a table of values. And here in this case, we're just going to review that quickly. That's the basic method of graphing. You can obtain any identity function or parent graph. And usually you plug in for x values ranging from -2 to 2. So if we create make a table, working area here in the middle. And let's plug in -2, -1, 0, 1, and 2 for x. 8 minus 9 times -2 squared. So of course, recall order of operations. -2 squared 4. 4 times -9 is -36. And then plus 8. So that's going to give you -28. And then we plug in -1 for x. That will yield -1. And keep going, plug in 0. That's going to give you 8. And if you will recall, this is a quadratic, because of course it has the exponent of 2 on x. A quadratic function is symmetric, so you will actually see this symmetry in your table as we go down. So here you have -28, -1. Then when you plug in 1, you're also going to get -1. When you plug in 2, you're going to get -28. All right, now of course, just plot those points. Notice that your y coordinate is it goes very small to -28. So on the y-axis, I would go by increments or a scale of 2, or maybe a scale of 4. In my case, I'm going to go by 4 because my y-axis is given to me very small. So let's go ahead and start plotting those points. So we have -2 x value, -28. All right, here's 28. Okay, so there's -2, -28, and then we have -1. -1 is going to be very small since I chose to go by 4 on the y-axis, or by an increment 4. And then we got 0, 8, which of course is your y-intercept. 0, 8 is going to be here. And then 1, -1, once again, very small. I gotta figure out once. I gotta play around with that and figure out once in that, but you should have a point here, as you see me trying to make. All right, then 2, 28, 2, and then -28 is gonna be here. All right, you guys get the picture. You've plotted plenty of points before, plenty of graphs. All right, let's move on. This All right, the next thing we're going to talk about is x and y intercepts. And of course, as you recall from Algebra 1, Algebra 2, these are points where a function crosses the x or y axis. And as stated, the best way to represent x and y intercepts are as ordered pairs, because that's what they really are. A lot of times students want to say, oh, the x-intercept is 3. Yes, you're correct. However, you would write it as an ordered pair. So for example, part A, x-intercept is -3. So the x-intercept is -3. So we would say -3. And then in any x-intercept, the y-coordinate is always 0. Your y-intercept is 5. And of course, for your y-intercept, your x-coordinate is always 0. In part B, you do not have an x-intercept. No, this graph doesn't cross the x-axis at all. Your y-intercept is 4. So we would write that, of course, in ordered pair form as 4, 0.
If there's a custodian in the building, could you please go to the front office to meet a new team member? Any custodian in the building, please report to the front office to meet a new team member. Thank you.
Okay, I apologize about that. All right, in this particular slide, we see various types of graphs, of course, and I think you guys know, I shouldn't have to reiterate that fact, how to pick out an x-intercept, where the graph crosses the x-axis. Sometimes it may cross more than once. And as you see in the fourth particular graph, where it crosses the y-axis 3 times. So in some cases, you may have no intercepts, you may have one of each, so on. So always be mindful of that. All right, in this particular slide set, I just want to go over, make sure you understand basic vocabulary. In math, I think it's very important that you understand what the wording means. I always tell people that math is pretty much like a foreign language sometimes. It can be. And number 1, in the rectangular coordinate system, the horizontal line is called the x-axis. And of course, in the rectangular coordinate system, that would mean we call the vertical number line the y-axis. In the rectangular coordinate system, the point of intersection of the horizontal axis and the vertical axis, what do you call that middle point? The origin. The axis of the rectangular coordinate system divides the plane into regions. We've already talked about this, called quadrants. And there are quad, of course, meaning 4. The first number order pair is called the x coordinate or the abscissa. The second number in order pair is called the y coordinate or ordinate. So abscissa, that's kind of an abstract term, abscissa and ordinate. You don't hear that a lot, but you need to be familiar with it in case you do hear it again. Okay. The order pair of 419 is a solution to the equation because when you plug in, you get a true statement, and we've discussed that. The x coordinate of a point where a graph crosses the x-axis is called the x-intercept, and the y-coordinate of such a point is always the y-intercept. Or the y-coordinate rather is always 0. When you're on the x-axis, your y-coordinate is always 0. So the y-coordinate of a point where a graph crosses the y-axis is called a y-intercept. The x-coordinate is always 0 in that case. Okay, here we're going to graph these two equations. And we can actually graph just one. If you recall anything about transformations from graphs in a prior class, on number 13, notice that your parent function would be y equals x squared. So we can make a table for that graph. All right, so let's graph this first one. If you substitute in, of course, 1, -1, so let's substitute in -2 for x. So we have -2 squared, +4, 4 minus 2, 2. So we're going to have a point at -2 and 2. And then we substitute in -1, -1 squared minus 1. So -1 squared is 1, and then that's going to give us -1. And then 0, -2, and 1. Of course, here you see your symmetry again for your points. So therefore, when you plug in all right, and then you're just going to connect those. Notice that this graph has actually been translated how? It's been moved down 2 places. So of course, number 14, where you see x squared plus 2, what do you think? How do you think that graph's going to be translated? Of course, it's going to move up 2 places. Recall that your parent graph for a quadratic, it would pass through this would be your parent graph, approximately. So they're taking your parent graph, shifting it down 2 places. Anytime you see a number added or subtracted at the end, such as -2 and +2 here, added or subtracted overall to your equation, then it's going to, that's a vertical shift. So vertical shift. You can use that shortcut and knowledge to help you later on. All right, same case here. Let's graph. So what do you think your parent function would be in this case? Here our parent function is going to be the line y equals x squared, which travels through the origin in this case. And this is going to move your graph down 2 units. So once again, vertical shift down. This added value of 2 moves graph up 2 units. Okay. What? No, I was recording.
Since you're on first block, what are you gonna be doing?
No, what? Nothing.
My assignment's in, but I'm just gonna talk to you about some stuff, so I can write it down,
Okay.
because they've already left me, so I just.
All right.
That's how it goes. Thank you.
You're very welcome.
See you later.
See ya. Okay, these, of course, are absolute value graphs, and your parent function in this case is going to be y equals absolute value of x. And if you recall, the parent graph for that, I'm going to get my pen to work with me here. It, of course, is a V graph, starts at the origin, such as this case, roughly. Parent graph and the 2 and -2. Of course, the negative value multiplied in front here, anytime you see a negative value multiplied, whether it's a whole number in this case or a fraction, is actually going to flip your graph. So it's always going to reflect it or flip. So you're going to see when we graph that, it's going to flip it over the x-axis. Some cases you're going to have absolute value graphs that go either left or right. And you can have a reflection over the y-axis. All right, in the top one, 2 times the absolute value of x. Well, we're taking every, what?
Are you recording?
Yeah. And so we've got y equals 2 times value, absolute value of x. And of course, I mean, you can do this in your head or you can create a little table, whichever. Let's just plug in some values. These graphs are symmetric as well. So I'm just going to plug in -2 and 2 so you can see what it does. So 2 times the absolute value of -2, that's going to give you 4. Because, of course, absolute value of -2 is 2. And then 2 times, I meant to make that positive 2. So 2 times absolute value of 2 is also 4. So we got points at -2 and 4 here, and then -2. So that graph's going to go there, and this graph is going to go here. So whole number multiplied outside, you can visually see that it actually vertically stretches your graph, or shrinks it rather. So it's going to actually pull that graph up vertically. And of course, you can use the knowledge that we've already created, the -2x, or the 2 times absolute value of x, and use the knowledge that's going to reflect it for the negative. This is really getting you a little bit ahead because we're going to dive into transformations of graphs in section 1.6. But if you will build up your knowledge, I'm telling you, you're going to see functions and graphs in every chapter. You will be so tired of graphing, unfortunately, by the end of it. We're not going to go through that one, but you can. That's one that you can go through, practice on your own. And cubic graph, parent graph looks like. All right, we'll graph it. So once again, if you just take some points and plug in for x, 2 cubed, it gets, the y values get large really quickly. So if I plug in 2 for x, then that's going to give me 8, and then of course I'll plug in 1, 0, -1, and then -2 cubed is also going to give me -8 rather. And then just connect that. Okay, the next couple of slides just make you really think. So in number 71, it's talking about if the product of a point's coordinates is positive, then the point must be in quadrant 1. So your directions in these problems, figure out if the statement is true or false. If the statement's false, make the necessary change to produce a true statement. In number 71, it's saying if you multiply your x and y, the point must be in quadrant 1. So let's think about that. Of course, you know that x and y can be positive and negative. Well, if you multiply a positive or negative, then your answer will be negative. If you multiply a positive and a positive, then you definitely, so here x of course is positive, here x is negative, y, of course some positive y. So think about if you took any pair of coordinates, multiply them. Well, if I take a negative and negative, I'm going to get a positive 2. So I can be either in quadrant 1 or I can be in quadrant 2. So number 71 is false. And that's why, because you can be either in quadrant 1 or quadrant 2. All right, let's look at the next one. It says if a point is on the x-axis, it is neither up nor down, so x equals 0. If you're on the x-axis, here, that is correct. You're neither up nor down. But think about it like this. If I'm on the x-axis, let's say here at 5, or at -5, your value of x is -5. The value that is 0 is actually your y coordinate, because look, on the y-axis, or in relation to the y-axis, it would be 0. So number 72 is false, and that y would be 0. On number 73, if a point is on the y-axis, its x-coordinate must be 0. So once again, if we're on an axis, more specifically the y in this case, it says the x-coordinate must be 0. And that's correct, because earlier we discussed a y-intercept always has an x value of 0. And your x would be 0 here. So that is true. Number 74, the order pair 2, 5 satisfies this equation. 3y minus 2x equals -4. Well, how do you check that? You simply take your x value of 2 and your y value of 5 and you plug in. And of course, this creates 15 minus 4. And we're trying to see if that comes out to -4. And you can easily see it does not. So that is false. And we just proved why. Of course, once again, this is just making you think, list a quadrant or quadrants satisfying each condition. So in 75, this is stating x times y has to be greater than 0. The product of an x coordinate and a y coordinate has to be greater than 0, which indicates it must be positive. So must be positive. Think about what is the only case or cases where we can multiply an x value and a y value and get a positive number. We can be in quadrant 1 because if I've got a positive x, if I have a positive x value here or a positive y, then I'm going to have a positive product. I can also be in quadrant 3 because if I take a negative x value and multiply it times its negative y value, I'm going to get a positive number. In 76, it states if you take y and divide it by x, your answer is less than 0. That's what this states. Y divided by x less than 0, which means it's negative. So think about in division, what are the only 2 cases where you could have a negative quotient or a negative answer? So I could either be in quadrant 2, and why is that? So for number 76, I can either be in quadrant 2 or quadrant 4. Those are the only 2 cases where I would have a positive x and a negative y. And if I divide a positive by negative, I'm going to get a negative. And same thing with quadrant 4. So we said quadrant 1 and 3, and then in 76 we said quadrant 2 and quadrant 4. All right, let's look at number 77. If you take x cubed greater than 0 and y cubed less than 0, so x cubed being greater than 0, let's think about that. It's saying that we take any number x, you raise it to the 3rd power, and you're always going to get a positive value. So the only case that can happen, I've got negative x's here. Well, if I raise a negative number to the 3rd power, it's always going to be negative. So I know I'm not using quadrant 1 or quadrant 3 in that case. Says, and I take y cubed and it's less than 0, meaning that I take a y value, raise it to the 3rd power, and it comes out negative. Well, of course, the only case is here. So I've already said I'm not using this part of the x-axis because it would not satisfy this part. And now I know I'm not using this part of the y because it's not satisfying this part. So that leaves quadrant 4. I have, if I raise any of these x values to 3rd power, it comes out positive. Raise any of these y's to third power, it comes out negative. So the only quadrant in this case is quadrant 4. In number 78, last but not least on this slide, this actually reverses number 77. If you take x cubed, or they're telling you x cubed comes out less than 0. Well, I know I'm definitely using this part of the x-axis. Y cubed has to be positive, so this part, so it must mean I'm in quadrant 2. Okay, these are pretty simple. Read these graphs. These are just time versus something happening type graph. So in this particular case, we're talking about time and the amount of snowfall. We'll recall time is always independent. You can't change time, even though we wish we could at times. We wish 2020 would hurry up and move along. But so what they want you to do in this case, you've got 4 graphs, 4 situations. We're going to match the graph that corresponds to your situation. So in number 75, as the blizzard got worse, the snow fell harder and harder. So that, of course, is meaning that as time goes on, snowfall is going to get higher. The amount of snowfall is going to get higher and higher. So time progressing. Notice that in part A, that has a positive correlation because time is progressing. Time's progressing here, and the amount of snowfall is definitely increasing higher and higher. So that looks like a good possibility for 79. And then in part B, okay, time, of course, is increasing. Your amount of snowfall is increasing at a constant rate, and then all of a sudden here, what happens to it? In this case, where you see the flat horizontal part of your graph, that means that your snowfall, did it fluctuate at all? Right, and then, so here, there was no snowfall at all in this time, 0. It didn't go up, it was constant, so there was no snowfall at all. Then on this case, it started slowly rising back up. So in part C, same thing. Snowfall, you have snowfall here, and then all of a sudden no snowfall because there's no change in distance according to this axis. And then it starts again. Time, or in part D, as time increases, notice that snowfall's getting, it's pretty steady, but then what is it doing? All of a sudden it's starting to taper off. So it seems like that snowfall is stopped coming down. So in 79, as time goes on, the graph that corresponds to the snowfall is harder and harder is part A. Part number 80, the snow fell more and more softly, meaning that it tapered off. So once again, if you'll look in graph D, the snowfall starting to taper off and getting less and less. So number 80 is D. Number 81, it snowed hard, meaning that you're going to have a very steep snowfall, steep line, but then it stopped. After a short time, the snow started falling more softly. So snowed hard, steep line, stop, flat line, it's falling softly. So number 81 is B. And number 82, it snowed softly, then it stopped, then it started falling hard. So snowed softly, of course, is going to have a very, not a steep line at all. So if you look and see, it, of course, last but not least, and matches up. All right, the next thing, we're going to switch gears here. If you recall, buying a graphing calculator is definitely optional, However, once we get back into the building, or you guys can get back into the building and we start meeting in person, I will let you use the classroom set that I have and we'll work with them all throughout the year. You can use Desmos.com to type in your graphs, or I've listed the website Symbolab. It's a really neat tool if you don't have one, but it's definitely optional. But you still need to know what the information looks like that you might see in the graphing calculator, because it is listed in the book frequently. Throughout pre-cal, you will see these brackets that I've got listed here for you. See that -10, 10, 1. This is actually your dimensions for your Cartesian grid in your graph. So for example, look here. This will tell you what your X axis should go by. This tells you what your Y axis should go by, which I've got it listed here as well. This is called your viewing window. They will give you these brackets in any particular problem set. You are required to change the dimensions so that you can visually see your graph best. These dimensions are going to tell you what your X axis, how far your X axis should go to the left, which is your X min, how far left it should go. X max is how far to the right your graph should go. This last number is your scale, meaning that your X axis is going to go by ones in this case. Sometimes, of course, that's 2, 4, 3, whatever. Your Y axis window will always be second. And once again, this first number is always your Y min, how far down your Y axis should go. Y max, how far up Y axis should go. Y scale is going by 1s, 2s, 3s, whatever. In your calculator, in a graphing calculator, this is what it looks like. And it'll always have X min, X max, X first, and we don't really ever worry about X res. You have some homework problems in this set that give you a table of values, and that's what we're going to look at next. Okay. You don't have to practice typing these in a graphing calculator. However, if for some reason you already have one or you went ahead and made the purchase, this is how you type them in. And I'm showing you on a TI-89, but it works very similarly for a TI-84 that I also put pictures of in your syllabus. Okay, so if you want to type in, let's say y equals x squared divided by 9, then in the top corner, usually here on your graphing calculator, there's a y equals key. Then you will notice that your calculator is always set up to where y has to be solved for. So for example, if we have x equals y squared minus 9, and you want to type that in your graphing calculator to see what it looks like, you would have to solve that for y. So add 9, then you would have to take the square root, and recall taking the square root, you would have positive negative root x plus 9. And that's what you would have to enter. You would have to enter one line as, this is way more in depth than what so don't stress about this, but I'm just helping those of you that might already have it. You would have to type in both these equations, positive root x plus 9, negative root x plus 9 here and here. Make sure that plot 1, plot 2, plot 3, none of those are highlighted. That's for BIMER and stats. Okay, next, once you've got the equation in your y equal area, then, oh, I forgot to tell you this. You will want to know where your X button is. Sometimes you will see it, but sometimes there's this key that has X, T, theta, N. So you'll hit that to get your X variable. Then you'll press second window to graph it. here, and you should see it. All right, now here's the neat thing. In your case, you will be given a table of values that match up with your function. And what these values mean, all right, I actually took these problems from your homework set for section 1.1 and 1.2. Let's say that I type in some equations in my calculator and I get this table of values. It says which equation corresponds to y2 in the table. Notice that you've got the same x values for both sets of y. So we got to determine which equation has the relationship from this x to that y. So let's just look. So from x to y2, the first x we have paired with y2, -3, 5. We've got 0, 2 is also a pair. And then, of course, we've got 2, 0, so on. You can pick any pairs you want. So you're trying to see which equation here would yield this relationship. All right, let's just go through. In part A, it states if I've got x, which in this case would be -3, and I add 8, I do indeed get 5. But let's look at the second pair. Of course, if I take 0 and plug in for x, add 8, I do not get 2. So it cannot be A. Let's look at B. If I take -3 and I plug in for x, subtract 2, I get -5, which is not +5. So it is not B. Option C. Take -3, plug it in for x. I would have 2 minus -3, which does make 5. So let's check the second. Let's check another pair. If I take 0, plug it in for x, 2 minus 0 does give me 2. And so that works. So you've got at least 2 ordered pairs that satisfy this equation. So C. All right, another type of question that you might get asked is, does the graph of y1 pass through the origin? Does the graph of y1 pass through the origin? Well, how would you know that? If you pass through the origin on the graph, of course, your x and your y are both 0. So I want you to look in the column of y1. Do you see a value of 0? Yes, we do here. So it's that simple. Just look in your y column. If you see a value of 0, that means it's crossing through the origin. And also you have to make sure that you've got the whole pair, 0, 0. So does the graph of y1 pass through the origin? Yes, because you've got both x is 0 and y is 0. You've got that ordered pair. At which point does the graph of y2 cross the x-axis? So y2 crossing the x-axis. Well, you need to think about what is the value of y when you're on the x-axis, and we discussed this in the previous slide, if you're on the x-axis, then y has to be 0. So go down to your column and let's find y 0. So here I'm looking for where y is 0. And I'm going to go back over to x. So 2, 0 is where the graph of y2 crosses the x-axis. So 2, 0. All right, and the next, we're getting into section 1.2.